previous video, we did this example where we got an answer of 6.45 as the equilibrium constant. Okay, and now today we're going to talk a little bit about what does that number actually mean. So remember, just looking at our previous examples, that the equilibrium constant expression is just the concentration of the products over the reactants, which means that if you have a number that's bigger than 1, then that means that the products, remember, on the top, products and reactants are on the bottom. So if you have a number that's bigger than 1, clearly what that means is that that number, the products, is greater than the reactants, which means that you have more products in your container, in your mixture, than you do reactants. Okay, remember, equilibrium does not mean that you have an equal amount of reactants and products. We talked about that in our first video. Okay, equilibrium just means that the rate of the forward and the reverse reaction are the same, but the amount of the products and the reactants can vary quite a bit. So if you have an answer of 6.45, that means that you have a lot more products than you do reactants, which you can actually already see. I mean, looking back at this example, notice we had 0.526 as the concentration of NO2 and only 0.0429 as the concentration of N2O4. So we had way more product than we did reactant, which again, that's what that number tells us, is it tells us if it's greater than 1, it means we have more product than we do reactant. And of course, if it's less than 1, then we have more reactant than we do product. Okay, and if it were equal to exactly 1, then that means that the ratio of the reactants to the products are exactly equal to each other. Okay, and that's basically what this talks about down here. Okay, if you have a large value for K, and really by large, that really just means greater than 1. Okay, if it's greater than 1, then what we say is we say that the equilibrium lies to the right, which again means that you have mostly products in your reaction, in your equilibrium mixture. Okay, if you have a small value for K, which again means less than 1, then the reaction lies to the left, meaning you have mostly reactants in that equilibrium mixture. Okay, and remember, going back to Unit 5, we didn't really do any calculations with this, but one of the equations that we saw was that delta G equals negative RT times the natural log of K. And K is always, as you can see here, K is either going to be greater than 1, less than 1, or equal to exactly 1. It's never going to equal 0. It's never going to be a negative number. Okay, K is never 0 or negative. Okay, it's either, you're just looking at, is it less than 1 or more than 1? And when it's more than 1, then again, the natural log of K is a positive number, but with that negative sign there, it means the delta G is negative. Okay, so when delta G is negative, the value of the equilibrium constant is greater than 1. And again, mathematically, we can see that there. If K is less than 1, then the natural log of a number that's less than 1 is a negative value, and delta G is therefore going to be positive. Okay, so when KEQ is greater than 1, when the equilibrium constant is greater than 1, delta G is negative. That is a thermodynamically favorable reaction in the forward direction. And again, it means there's more products than there are reactants. You can see that right here. Okay, KEQ is greater than 1, and when that happens, delta G is a negative value. Equilibrium lies to the right. You have mostly products. And again, you can see that in that equilibrium mixture, you absolutely have more products than you do reactants. Okay, when KEQ is less than 1, then delta G is a positive value. The equilibrium, we say, lies to the left. You have mostly reactants in your equilibrium mixture. Now, again, like we said before, equilibrium constants can change from one reaction to another. It's not going to be 6.45 like that one first example was. Sometimes you have equilibrium constants that are really, really small, down like in the negative 34th, negative 25th values, which are super small. Sometimes you have really, really big equilibrium constants, like in the hundreds or even the thousands. Okay, so from one reaction to another, the equilibrium constant could change because, again, remember, it's just a comparison of what your amount of products are versus your amount of reactants. So if it's a really, really small number, then yeah, you have hardly any products at all, and you have lots of reactants. If it's a really, really big number, then you have, again, mostly almost all products and very, very little reactants. And in fact, when K is really, really big, and again, when K is like maybe 50 or higher, basically you can just do stoichiometry with a problem like that. When K is really, really big, it means you virtually have no reactants left at all. And so if you're trying to do a problem like that, you can just pretend like this reaction goes all the way to the right. And so it's just like you can just do a regular stoichiometry problem with something like that. Okay, and again, the key is that the equilibrium constant is not constant, okay? And even within the same reaction, if you change the temperature, which we'll get to here in a couple more videos, if you change the temperature, the equilibrium constant will also change. So not only does it change from one reaction to another, it also changes when you change the temperature of the reaction mixture. Okay, when it doesn't change, though, is when you change your starting amounts of reactants and products. Okay, and this is where you kind of, the line kind of starts to get blurred between what's a reactant and what's a product. Because you can start with some N2O4, and then of course the reaction is going to start by proceeding to the right. But if you don't have any NO2, the reaction has to start by going to the right. Okay, but theoretically, couldn't you also start with some NO2, and then the reaction is going to start by proceeding to the left by making some N2O4 until it reaches equilibrium? Absolutely yes. So it's kind of like, well, wait a minute. So which one's a reactant, which one's a product? Again, anytime you have something on the left-hand side, the left-hand side is the reactant side, the right-hand side is the product side. That's all that you need to remember. But could you technically start with some product? Absolutely you could. I mean, look down here. Look at the first 3 experiments that they do. The first 3 experiments, they don't start with any N2O4. They start with 3 different amounts of NO2. So they start with the product each time. And notice that to reach equilibrium, obviously you're starting with no N2O4, so the reaction is going to start by going this way until it reaches equilibrium. So notice that the N2O4 goes up. Notice that from this number to this number, the NO2 obviously has to go down because the reaction's going back to the left. But the more important thing is it doesn't matter what amount you start with. In the first 3 trials, we started with this much product. And in the 4th experiment, we started with some reactant. And again, no product. And we could have started with some reactant and some product at the same time. We could have had, for example, 0.519 of this and 0.125 of this. Okay, what you're going to find is that the ratio of reactants to products, once you reach equilibrium, is always going to be the same. Okay, that's also going to be either 6.45 or 6.46. Okay, so it doesn't matter. Your starting pressures or your starting concentrations don't matter. Once you reach equilibrium, the reaction is going to get to a point where the ratio of the reactants to the products, the equilibrium constant, right, is always going to be the same value. Okay? So, doesn't matter your starting concentrations, all that matters is that once you reach equilibrium here, you plug those numbers into the equation, you're always going to get the same value for the equilibrium constant, unless it's a different reaction or you've changed the temperature.